The following is an introduction and procedural outline to the synthesis of para-aminobenzoic acid, also known as PABA. PABA is a chemical found in the enzyme cofactor folic acid, which is crucial for proper brain function as well as the development of the CNS during pregnancy. It is also seen in some foods, including grains, eggs, milk, and meat. It is often seen being used in sunscreens because of its ability to absorb the ultraviolet component of solar radiation. Sulfonamide drugs are structurally similar to PABA. This allows them to replace PABA in folic acid, rendering it deactivated. In turn, the bacteria who are using this folic acid to produce nucleic acids will deactivate, stop growing, and the body's natural immune system can then take them out.
The synthesis to create para-aminobenzoic acid consists of three main steps: a protection, an oxidation, and hydrolysis, or deprotection. Let's start with a definition of protection. Protection is a step taken to reduce the reactivity of certain functional groups. In the case of para-toluidine, the functional group in question is an amino group. Step 2 of this reaction is an oxidization step using potassium permanganate, which is a strong oxidizing agent. So if we were to do this step without previously protecting the amino group, as shown on the bottom, both our methyl group and our amino group would oxidize fully to a nitro group and a carboxylic acid. Therefore, the first step of the reaction must be protecting the amino group on the para-toluidine. Then, once the reactivity of that has been lowered, we are able to oxidize the methyl group and then use hydrolysis to remove the acetyl group, leaving us with our para-aminobenzoic acid. For step 1 of this reaction, we need to protect the amino group on our para-toluidine. We will be doing this through acetylation. To do this reaction, we're going to be reacting our para-toluidine with acetic anhydride in the presence of an acid as well as sodium acetate. The basic mechanism for this is shown below. What this will leave us with is N-acetyl P-toluidine. So we now have our protecting group on our amine, which is going to greatly reduce its reactivity. Therefore, it will not be as easily oxidized. So we are able to do an oxidation in the next step and only affect the methyl group.
In the second step of this reaction, we will be oxidizing the methyl group to a carboxyl group using potassium permanganate as our oxidizing agent. This is possible because substituted benzoic acids are extremely stable. Therefore, alkyl groups attached to aromatic rings are readily available for oxidation. So to do this, we'll be taking N-acetyl P-toluidine and reacting it with 2.8 grams of potassium permanganate, and then later acidifying the solution with excess 20% sulfuric acid. What this is going to do is it is going to oxidize our methyl group to a carboxyl group. At the same time, it will be reducing our manganese from manganese 7 to manganese 4.
For the second step of our reaction, we are going to be oxidizing our N-acetyl P-toluidine to para-acetoaminobenzoic acid, using potassium permanganate as our oxidizing agent. What this is going to do is it is going to oxidize our methyl group fully to the carboxylic acid. Note, it is not going to affect the amino group because of the previous protecting step. In this reaction, potassium permanganate changes to manganese dioxide, and in turn goes from manganese 7 to manganese 4. Remember, something that oxidizes has to be reduced in return. There will always be a give and take. The final step of this reaction is a deprotection step. This is necessary because now that we have completed our oxidation successfully, the only thing standing between us and our desired product is our protecting acetyl group, so it must be removed. We will be doing this through an acid-catalyzed hydrolysis, the mechanism of which is shown below. The basic goal of this reaction is to remove our protecting group without affecting the rest of our molecule. So if we look at the mechanism, we're starting with a protonation of the carbonyl group, using one of the acids as a proton donor. This is going to allow water to attack the carbonyl carbon, and after some more deprotonation, leave us with a diol. Now these diols are very similar to our byproduct, acetic acid. After another protonation of the nitrogen and some electronic rearrangement, we remove the group that will then go on to become our acetic acid, leaving us with fully deprotected para-aminobenzoic acid. So we have now successfully removed our acetyl group after having our oxidation done, so this is a perfect example of protection chemistry. So now we will quickly go through a brief outline of the procedures by day. So day 1, we're going to start with the preparation of our para-acetoaminobenzoic acid. We will start by placing 0.80 grams of the para-toluidine in a 50 milliliter Erlenmeyer. We will then add 20 milliliters of water and 0.8 milliliters of concentrated hydrochloric acid. We will warm on a hot plate while stirring. If there is any color left, we will add decolorizing charcoal. While this is stirring, we will prepare a solution of 0.72 grams of sodium acetate in 2 milliliters of water. We will warm the solution to 50 degrees Celsius and add 0.85 milliliters of acetic anhydride. You must stir the solution rapidly using a stir bar and add the sodium acetate solution. After this is allowed to mix, we will cool it in an ice bath and then filter the white solid via vacuum filtration. Next, we will place the wet N-acetyl P-toluidine in a 100 milliliter round bottom flask. We will add 1.4 grams of potassium permanganate and 30 milliliters of water to the flask. This is for the oxidation step. We will add a stir bar and a reflux condenser. We will heat to boiling while stirring for 20 minutes. In other words, we will reflux for 20 minutes. We will remove it from the heat and allow it to cool before adding an additional 1.4 grams of potassium permanganate. We will then reflux this for an additional 20 minutes. We will vacuum filter the hot solution through Sealite and wash the precipitate with hot water. We are then able to cool the filtrate and acidify with an excess of 20% sulfuric acid. We will then dry in an oven before storing in our drawers for the next week. For the second day of the lab experiment, we will start by obtaining a yield and melting point of the previously made para-acetoaminobenzoic acid. We will then make a 50-50 HCl to water dilute solution by adding 2.4 milliliters of concentrated hydrochloric acid into 2.4 milliliters of water. Remember, add acid. We are then able to place the prepared para-acetoaminobenzoic acid with a few boiling stones, 2 or 3 should be fine, into a 25 milliliter round bottom flask. We will then attach a reflux condenser and add our 50% hydrochloric acid solution. We will gently reflux this for 30 minutes. There should be no vigorous boiling. We will cool and transfer this mixture to a 50 milliliter Erlenmeyer. We will add 1.5 milliliters of water and then make the solution slightly alkaline with concentrated ammonium hydroxide. Slightly alkaline, we're looking for pH 8 or 9, barely off of neutral. We will then chill it in an ice bath, filter, and then we will be able to determine our yield and melting point of our para-aminobenzoic acid. A few final notes. Firstly, this is a 2-part experiment that will take place over 2 separate lab periods. On the first day, we will be preparing through the acetoaminobenzoic acid and placing it in a drying oven. Then, we will put it back in our drawers to wait until the following week. The second day, we are going to be obtaining a yield and melting point of that para-acetoaminobenzoic acid, and then we're going to use it to prepare our para-aminobenzoic acid. Then we will obtain a yield and melting point of the final product, and remember to calculate the yield from the initial starting material, para-toluidine. Also remember that para-toluidine is a suspected carcinogen, so please be careful and use gloves and goggles when handling. A final note, when you are diluting acids, you want to always add the acid to the water. Remember, add acid AA. This is a very important step.